Very good morning, students.
Good morning.
Good morning, sir.
Good morning, all of you. So, without wasting any time, let us start with the discussion. Last class, we have been seen about how difficult it is to substitute a nucleophile on an aryl halide, and we have seen the reasons also. The reasons why nucleophilic substitution on aryl halide is difficult is, first of all, you have carbon halogen bond exhibiting partial double bond character. The electronegative difference between sp2 hybridized carbon and the halogen is less when compared to the electronegative difference of sp3 hybridized carbon and halogen. The phenyl cation is unstable. SN1 SN2 are not possible. And ultimately, we can say if you try to think of the nucleophilic attack, it will experience more repulsions. So because of this, a nucleophilic aromatic substitution is going to happen. SN1 SN2 are not possible. The nucleophilic aromatic substitution by addition elimination type reaction is going to happen in the case of aryl halides, and that will also happen at some high temperature and pressure conditions. So this is what I am talking about, nucleophilic aromatic substitution SNAR by addition elimination type. It has a different mechanistic path when compared to the general SN1 or SN2. Nucleophilic aromatic substitution can occur when strong electron withdrawing groups are present at ortho and para positions. With respect to halogen atom, how the reaction goes, if you try to think of that part, obviously you can easily understand what is going to happen and do we require electron donating groups or electron withdrawing groups at every point. Yes or no? Only thing we have to understand is how the reaction is going to move. How the reaction is going to move. So let us take the same scenario, students. Let us take the same scenario of electrophilic substitution reactions. Like we have chlorobenzene, and at the para position you have nitro, that is NO2 group substituted, and we are treating this with NaOH 443 Kelvin H plus. You are getting respect to OH substituted by chlorine. So what is going to happen in the first stage is, whatever the chlorobenzene you have, I am just writing the reaction with respect to chlorobenzene without any substitution, and we have OH minus, right? The OH minus will try to attack this particular carbon, and instead of carbon chlorine bond cleaves, the carbon carbon pi electron density will be donated to the next carbon, that is ortho position, generating this type of intermediate. OH will be placed here and Cl will be as it is. OH is now going to attack the electrophilic carbon. Although the electronegative difference is less, still this carbon is electrophilic because it is connected to halogen atom. OH is going to attack this particular electrophilic carbon. Carbon chlorine bond leaves. This is going to be the rate determining step because it is slower step. Why it is slow? Because of nucleophile experiencing repulsions. Now it resembles like a carbon ion, and it will exist. It will exhibit the respective resonating structures. So negative charge coming into pi electron density moving away. Negative charge will be here now. We have chlorine and OH. Again, if you try to draw the respective resonating structure, negative charge coming into pi electron density moving away. So where we are getting a negative charge? Where we are getting negative charge? At ortho and at para positions. Finally, negative charge comes into carbon chlorine leaves. So you will be having the scenario like this. And you may also think like, sir, why can't the negative charge moves in the resonating structure and why it is losing? Why can't it will directly go in this fashion? OH minus comes here, chlorine. That can also be possible because all these are fast steps. All these steps are fast, so all these can be accepted. Only the first step is the rate determining step. Fast steps can occur at a greater rate, so we can't decide actually from where the negative charge is coming and chlorine is leaving. So these are all the resonating structures. These are also called as Meson-Hammer complexes. These are also called as Meson-Hammer complex. So the rate of nucleophilic aromatic substitution reaction will be depending upon the stability of this Meson-Hammer complex. So when this complex is stabilized, if you look at this complex or resonating structure, you are getting negative charge at ortho and para. If you have electron withdrawing groups at ortho and para position, they will remove the charge, thereby increasing stability. Yes or no? So nucleophilic aromatic substitution can occur when strong electron withdrawing groups are present at ortho and para position with respect to halogen. Because at ortho and para we are accumulating negative charge. If you have strong electron withdrawing groups at ortho and para, they will withdraw the negative charge, they will withdraw the electron density, thereby increasing the stability. Understood this or not?
Yes, sir.
Yes, right. So greater the number of electron withdrawing group, greater will be the rate. Like if you have only one NO2 group at the para position and chlorobenzene, you have to treat with NaOH. OH minus acts as a nucleophile, nucleophilic aromatic substitution happens, but the temperature you have to maintain high, 443 Kelvin, and then you have to do the H plus acidification. If you maintain the high temperature like 443 Kelvin, then this reaction will happen. But if you have two electron withdrawing group, two NO2 group at ortho as well as at para, the temperature has been come down, you can see 368 Kelvin. You will get the same substitution like OH is going to be substituted by chlorine. If you have the other ortho position also occupied by NO2, if you have the other ortho position also occupied by NO2, so this in this scenario, all the ortho and para positions are completely occupied by electron withdrawing groups. So the resonating structure is highly stabilized. Because of that, this reaction will simply happen upon warming. You don't require very high temperature. Is that point clear, students? The electron withdrawing groups present at ortho and para positions, they stabilize the complex. If the complex is stabilized, then the reaction is going to happen at a greater rate and under normal conditions. If the complex is not so stable, then you have to maintain high temperature and pressure to happen the reaction. So the mechanism that operates in these reactions is an addition elimination type. Why I am calling it as addition elimination? Because in the first step OH is added, and after that the chlorine has been eliminated. The addition of OH and elimination of chlorine is not happening simultaneously. So addition occurred, then elimination occurred. So that is why it is an addition elimination type mechanism. Look at the mechanistic approach. The same thing whatever we have explained. OH minus attacking this particular carbon, pi electron density moving away, generating you have carbon, chlorine, carbon OH, negative charge. You can draw the respective resonating structures. Resonating structures you can draw in this manner. These are all said to be Mesenheimer complex or carbanion systems. And from all these, the respective loss of chlorine occurs fastly because that is not the RDS. Fastly negative charge comes into carbon, chlorine leaves. I have drawn from this resonating structure. You can draw from this also. You can also draw from here. Yes or no? And if you observe carefully, we still have Cl minus in the reaction mixture which can pick up this proton or not. OH bond is there, Cl minus can pick up this proton to form the respective phenoxide, substitute at the para position. And that is why we are doing the acidification in the final stage. Whenever you do the acidification, like second stage is acidification, the phenoxide ion will try to pick up this proton, forming the respective phenol system, substitute at the para position. So these are nothing but your mechanism for addition elimination. Mesenheimer complex is the intermediate, not the SN1 type or SN2 type. Note, carbanion intermediate is formed. Rate of reaction is directly proportional to stability of Mesenheimer complex. More stable the Mesenheimer complex, more will be the rate of that particular reaction. So how the stability of Mesenheimer complex can be judged? Based on the number of electron withdrawing groups present at ortho and para positions. Electron withdrawing groups present at the ortho and para position with respect to leaving group increase the rate of reaction as they stabilize the Mesenheimer complex. Is everything clear, students, regarding addition elimination type?
Yes, sir.
Yes, right. Very good. So compare the rate. First question, compare the rate of following towards nucleophilic substitution reaction among these two
A
compounds.
greater than B.
Obviously, more number of electron withdrawing groups, more will be the rate of nucleophilic aromatic substitution. So here we have 3 NO2, whereas in the second compound we have only 2. Compare the rate in the second example.
A greater than C next B.
A greater than C next B. Why?
Because it's meta.
Yeah, meta position NO2 means NO2 is electron withdrawing only. If it is presented ortho and para, it withdraws electron density by resonance. If it is presented meta, it withdraws electron density by inductive effect. Okay.
Inductive.
So how, it is always electron withdrawing group only or not? NO2 group is an electron withdrawing group. NO2 presented ortho and para withdraws the electron density by resonance. But NO2 presented meta will withdraw the electron density just by inductive effect, but it is still withdrawing the electron density. So obviously meta nitro chlorobenzene, that will also be having greater rate towards nucleophilic aromatic substitution when compared to simple chlorobenzene, because at least by inductive effect it is withdrawing the electron density. Okay, it is not donating if it is at meta position, it is still withdrawing only, but by inductive effect, not by resonance.
Okay.
Okay. So same, compare rate of the following towards hydrolysis means again same, nucleophilic aromatic substitution occurs. This is the correct rate. Compare rate of the following towards nucleophilic substitution. This is compound A, compound B, compound C, compound D. Compare the rate. A, B, C, D, 4 compounds.
DABC.
D, A, B, C. C is least, you are saying, right?
Yes, sir.
Why?
Sir, because nucleophilic substitution does not act on 3-degree carbon. 3-degree halides.
3-degree halides, nucleophilic substitution will not happen. Who told you that, Faizan?
Sir, due to
Nucleophilic
steric and
no, they are saying nucleophilic substitution only. Okay, don't confuse. Nucleophilic 3-degree alkyl, if you take it, it proceeds to SN1. If you take 1
yes, sir,
degree, it
I
proceeds to SN2. Okay, so you should not get confused. If you take 3-degree alkyl halide, then it will proceed through SN1 reaction, leading to the formation of carbocation. So in the compound C, it will be having the highest stability or not, 3-degree carbocation. We are doing hydrolysis.
Yes.
So CH3, C, CH3, CH3 plus. So C will be having the greatest. First, you have to eliminate A and B, because in C and D you have alkyl halides, which will be having greater tendency to undergo nucleophilic substitution when compared to aryl halides. So among C and D, C will be having greatest. After C, you will be having D, because here you are getting 3-degree carbocation, here you will be getting 2-degree carbocation, CH3, CH plus, CH3. Okay, CD. And you have to place A and B set after the C and D set. C will be greater than D, because in C we have 3-degree carbocation, in D we have 2-degree carbocation. In A and B, it is proceeding through nucleophilic aromatic substitution, that is addition elimination type. In the addition elimination type, more groups at the ortho and para positions, more electron withdrawing groups at ortho and para positions, increase rate. So after C we have D, after D we have A, after A we have B. Okay, don't get confused. Very simple question. They were not asking about SN2 specifically. They were just asking about nucleophilic substitution. So it can be SN1, SN2, SNAR. In the compound A and B, it is nucleophilic aromatic substitution. In compound C and D, it is SN1. So that depends whether it is SN2 or SN1 or SNAR. That depends upon the substrate. Got it?
Yes, sir.
Yes, right. So aryl halide without electron withdrawing substituents do not react with the most nucleophiles under ordinary condition. This is important. If you have taken aryl halide like chlorobenzene, you are treating this with NaOH, like Na plus OH minus acts as a nucleophile. This OH minus cannot directly substitute this particular carbon chlorine bond. Why? Aryl halide without electron withdrawing substituents. If there is no electron withdrawing substitutions, there is no stabilization of the Mesenheimer complex. If there is no stabilization of the Mesenheimer complex, how come the reaction happen? So for this reaction to happen, we require very, very high temperature and high pressure. So then only this reaction happens. At normal condition, this won't happen. Like chlorobenzene treated with KCN also no reaction, with NaOH also no reaction under ordinary conditions. But for this reaction to happen, we can maintain temperature like 623 Kelvin, 300 atmosphere. that is NaOH in the presence of very high temperature, 623 Kelvin and 300 atmosphere. Second acidification, if you do, you are getting OH minus substitute. How this reaction happens? Again, the same Messenheimer complex, carbon chlorine bond. So OH minus is going to be attacking this particular carbon. Pi electron density moves away. This is slow step, which is nothing but the rate determining step. You get negative charged ortho, chlorine and OH. We can draw the respective resonating structures, and the fast elimination is going to happen. Fastly, the elimination occurs. You generate this particular intermediate, this particular product, and this will happen at high temperature. And Cl minus, which is lost, that can try to pick up the proton to form the respective phenoxide, O minus. So you have to do the acidification in the last stage, so that whatever the acidification you are going to do, you will be generating respective phenol back. This process is nothing but your Dow's process. Preparation of phenol from chlorobenzene by treatment with NaOH at high temperature and pressure, followed by acidification, is known as Dow's process. Temperature is 623 Kelvin and pressure is 300 atmosphere. That conditions you have to remember. First, you will be getting respect to sodium phenoxide if you do only treat with first process, that is NaOH. You are getting phenoxide, which will have electrostatic force of attraction with Na plus ion, sodium phenoxide. And that sodium phenoxide upon acidification forms respect to phenol. So this is nothing but your Dow's process. Is that clear, students? And this is, yeah, and this is one of the method of preparation of phenol. Yes or no? Next, in the next chapter, alcohols, phenols, ethers, we will be studying about the preparations of phenols also, and this is one of the method of preparation. Reaction with metals. In the reaction with metals, we have seen the reaction like Wood's reaction we have seen. Before the Wood's reaction, we have seen the preparation of Grignard reagents, and after that we can see two different reactions like Fittig reaction and Wood's Fittig reaction. Fittig reaction means, Wood's reaction means alkyl halides only will be forming respect to higher alkane. Fittig means aryl halides will combine with to form biphenyls. Wood's Fittig means you will be getting alkyl aryl scenarios, like alkyl halide and aryl halide will be taken. They will be fused together to form substituted benzene derivatives, alkyl substituted benzenes. Aryl halides treated with sodium in the presence of dry ether, it will form respective biphenyl system, and the proposed mechanism is again free radical path. Wood's Fittig reaction, you can take an aryl halide and alkyl halide, treat with sodium in the presence of dry ether. Whenever you do Wood's Fittig reaction, you are going to get mixture of products, students. You are going to get mixture of products. Out of those mixture of products, the aryl halide and alkyl halide, wherever they have reacted to form substituted benzene, alkyl substituted benzene derivative, that is going to be the major, and the other two are side products which can also be obtained. These are nothing but side products, biphenyls, alkanes, and substituted benzene derivatives. Like if CH3, C6H5 is there, that is called as toluene. Methyl benzene, ethyl benzene, isopropyl benzene, like that different kinds of alkyl substituted benzenes can be obtained whenever you try to do Wood's Fittig reaction. But the disadvantage is you are going to get a mixture of products where the separation becomes again difficult. Then look at the polyhalogen compounds CHCl3, CHI3, chloroform and iodoform. Chloroform, if you look at chloroform, it is used as anesthetic, and pure chloroform, if you want to check the purity, the pure chloroform will not react with AgNO3. That means with AgNO3, the pure chloroform will not have any reaction. But if you have impure chloroform, that will react with AgNO3 to form AgCl. Why this pure chloroform will not react with AgNO3? Because the carbon chlorine bond is a stronger bond. If you treat a pure iodoform with AgNO3, it will form AgI. But a pure chloroform will not react. Okay, because carbon chlorine bond bond is stronger and not easy to break and not easily broken. But carbon iodine bond can be broken. Okay. Before being used, it was tested with aqueous AgNO3. How the test is going to happen? If the chloroform is reacting with the AgNO3, then we can say that chloroform is impure. If it is not reacting with AgNO3, how do you know whether it is reacting with AgNO3 or not reacting? If it reacts, we will be getting a AgCl, which is a precipitate. And chloroform is highly dangerous. Chloroform is highly dangerous because it will be slowly oxidized by air in the presence of sunlight to form an extremely poisonous gas known as phosgene. Chloroform plus O2 oxygen in the presence of sunlight, it will form phosgene and HCl is going to evolve. That is why whenever you try to store chloroform, you might have seen in the laboratories, it will be always stored in dark bottles so that no sunlight will enter. And always the bottle of chloroform is completely filled. There should not be some empty space left out. You should not fill the bottle of chloroform half. Why? Because the other half is empty where air can be present. If it is completely filled, there will be no possibility for air. There is no space for air to occupy. Chloroform has to be stored in dark bottles and it has to be filled completely so that this oxidation is not going to happen. If this oxidation occurs, this phosgene, whatever it is going to develop, that is going to be the phosgene, whatever it is going to be obtained, that is going to be highly dangerous or poisonous gas. Okay, to prevent this, chloroform is stored in dark bottles and completely filled so that air is kept out of the reaction mixture or bottle. And if somehow, although you try to maintain dark bottle and you almost fill it completely, but there may be always a possibility for some amount of chloroform will react with air when you try to open the cap for usage. In that condition, sunlight may be there. Yes or no? It's not like storing separately. We have to use chloroform in different reactions. In that reactions, whenever in the process of usage, if the chloroform is exposed to air and sunlight, there may be possibility it will lead to the formation of phosgene. So to avoid that also, you will be adding some small quantity of ethanol. The ethanol is also added to chloroform so that whatever the phosgene obtained, that will react with ethanol to form diethyl carbonate. Also, some ethanol is added to chloroform so that phosgene formed can phosgene formed can be poisonous phosgene formed can be converted to diethyl carbonate. How does that reaction happen? Like whatever the phosgene we have, phosgene is C double bond O, CCl, CCl, and ethanol we are adding C2H5OH, C2H5OH. And can I say this carbon is more electrophilic or less electrophilic? This Cl, C double bond O, Cl, Cl, C double bond O, Cl. This carbon is more electrophilic or less electrophilic?
More electrophilic.
More electrophilic because the carbon double bond oxygen, the pi electron is moving away towards oxygen, and chlorine is also electron withdrawing group. But you can also argue, sir, chlorine lone pair of electrons are present on chlorine. If you try to include the resonating structures of lone pair of electrons in chlorine to C double bond O, the partial positive charge on carbon should be nullified or not? Yes or no? If you include the resonance of lone pair of electrons and halogen to the C double bond O, the partial positive charge developed on carbon has to be nullified. In that case, the electrophilicity of the carbon has been decreased. If the electrophilicity is decreased, the nucleophilic attack is not going to happen greatly. But we all know for halogens, the electron withdrawing tendency is great when compared to electron donation by mesomeric. So electron withdrawing is great. That is why whenever you're looking at halides like derivatives of carboxylic acid, in the derivatives of carboxylic acid, what are the derivatives we have? 4 derivatives: acid halides, anhydrides, esters, amides. In that, acid halides are more reactive. Acid halides are very highly reactive towards nucleophilic substitution by addition elimination. There also in the derivatives of carboxylic acid, you have the same nucleophilic substitution by addition elimination. Acid halides will be having greatest reactivity towards nucleophilic substitution because the carbon is going to be more electrophilic. You should not think of lone pair of electrons on chlorine into resonance. You should always think of chlorine as an electron withdrawing group greatly. After that, you will have acid anhydride, because in anhydride, the lone pair of electrons on oxygen in resonance with the two sides, two C double bond O's. After that, you have esters. In esters, also lone pair of electrons on oxygen, like in anhydrides, you can take CH3, C double bond O, C double bond O, CH3. So lone pair of electrons on oxygen in resonance, two sides. So net resonance has been decreased. In esters, we have only one lone pair, like only one resonance. In amides, you will be having least reactivity. Why in amides least reactivity? Acid halides, I am saying that chlorine is withdrawing the electron density or halogen is withdrawing the electron density, thereby increasing the partial positive charge. Acid anhydrides, esters, amides you compare. In acid anhydride, we have lone pair of electrons on oxygen in resonance with the two C double bond O. So thereby decreasing the positive charge is less. So this carbon is more electrophilic when compared to esters and amides. So after acid halides, it should be acid anhydrides. After acid anhydrides, compare esters and amides. Lone pair of electrons on oxygen in resonance, lone pair of electrons on nitrogen is also in resonance. But which is more electronegative when compared to oxygen and nitrogen? Oxygen is more electronegative. Oxygen being more electronegative, it can withhold the lone pair on it. Nitrogen being less electronegative, it will use its lone pair into resonance greatly. So nitrogen is using the lone pair greatly. So the positive charge, whatever present here, that will be least or not in amides.
Yes.
So this is the order of acid halides, acid anhydrides, esters and amides towards nucleophilic substitution by addition elimination type. With respect to the same logic, we can say this phosgene, whatever you have, we have two chlorines connected to C double bond O, both are electron withdrawing, thereby the carbon is going to be more electrophilic. You may ask a question, sir, why you are saying all this? Because whatever the alcohol we are taking, that is not a great nucleophile. The alcohol is not a great nucleophile. If the electrophilicity of the carbon is less, the nucleophilic attack is not going to happen. It will never happen. But here this carbon has more electrophilic nature, so lone pair of electrons on oxygen they can attack easily. No requirement of acid medium. So we have carbon chlorine bond. Carbon is now connected with CO minus, two carbon chlorine bonds as it is. Carbon also connected with oxygen. Oxygen one lone pair positive charge. OH bond as it is. Oxygen also connected with C2H5 group. But negative charge on oxygen is slightly unstable. So what happens? The negative charge on oxygen comes into the carbon chlorine bond. The chloride is going to be lost now. Loss of chloride occurs. We generate C double bond O CCl. Oxygen with one lone pair positive charge OH bond and C2H5. Let us proceed to the next page. We have C double bond O CCl. Oxygen lone pair positive charge one OH bond and C2H5. The Cl minus, which was present in the reaction mixture, that can pick up the proton. OH electron density is given to oxygen, developing CCl, C double bond O. Oxygen regain its lone pair, and oxygen is connected with the C2H5 group. Again, one more C2H5OH is there. C2H5OH. Lone pair of electrons on oxygen, they still attack this carbon. C double bond O pi electron density moves away. You generate CO minus. Oxygen lone pair positive charge OH bond. C2H5. Carbon chlorine as it is, and oxygen connected with C2H5. Again, what happens, students? The negative charge on oxygen comes into chloride leaves, loss of chloride occurs. We have C double bond O, oxygen with one lone pair connected with C2H5, positive charge and OH bond, and oxygen two lone pairs OC2H5. The chloride which is lost, that will now try to pick up this proton. OH electron density will be given to oxygen, generating C double bond O, OC2H5, OC2H5. It is nothing but diethyl carbonate. Yes or no? So small quantity of ethanol is added to phosgene to actually convert the phosgene to diethyl carbonate, which is actually less poisonous in nature. That is how the reaction is going to be done. That means we are not going to deal with poisonous gases. We have to reduce the toxic nature of phosgene. That means we have to convert the phosgene into some other species where the poisonous nature can be reduced. Is that clear, students? Yes, right. Iodoform. Iodoform is also used as antiseptic. Whenever the iodoform comes in contact with the skin, it forms I2, which has antiseptic properties. And as I have told you, pure chloroform will not react with AgNO3, but a pure iodoform will react with AgNO3 to form AgA, because you can say CI bond is weaker, so that can be easily broken. Okay, CI bond is weaker than CCl bond and CCl bond, so that is why the carbon iodine bond can be easily broken. If that can be broken easily, so AgA can be formed easily. Next comes the freons. Freons is chlorofluorocarbons. Chlorofluorocarbon compounds of methane and ethane are called freons. You can take CCl2F2, C2F2, Cl4. Chlorofluorocarbons like methane means CH4. You have to replace all the hydrogens by either fluorines and chlorines. CCl2F2. Similarly, C2H6 is ethane. You have to replace 6 hydrogens by the halogen atoms like fluorines and chlorines. C2F2, C2F4, Cl2. So these are nothing but freons. And where are these used? Freons? Refrigeration mostly. They are produced for aerosol propellants, refrigeration, and air conditioning purposes. Excess use of these will result in the depletion of ozone layer. The ozone layer, whatever you are going to have, that is going to be depleted whenever you are using excess of freons, because they are going to form a free radicals, and their free radicals are going to be reacting with ozone, and ultimately it will have the depletion of ozone layer. Okay. In the polyhalogen compounds, after chloroform, iodoform, freons, we will be having DDT, diphenyl trichloroethane. So how is it prepared? It is prepared by heating chloral and chlorobenzene in the presence of concentrated H2SO4. What is the formula of chloral, students? Chloral? Anyone?
CCl3CH.
Very good. CCl3CHO and chlorobenzene. So chlorobenzene and chloron, they are actually heated in the presence of H2SO4, and you will be getting DDT, and it is earlier used as an insecticide, but now its usage has been reduced. And this is the structure of diphenyl trichloroethane. How is it prepared? If you want to look at the mechanistic approach, you can just take chlorobenzene and you treat this chlorobenzene with or first you have to prepare the electrophile, right? Chloral plus H2SO4, what happens? CCl3, C double bond OH. If you treat this with H plus from H2SO4, lone pair of electrons present on oxygen, they will be attacking the H plus ion. As soon as they attack, you will get CCl3, C double bond O, oxygen with one lone pair, positive charge OH bond and CH bond, CCl3. And this upon treatment with the chlorobenzene, whatever you have, that is going to be attacking the electrophile now. This is the electrophile or not, because the pi electron is moving towards oxygen, developing COH and a positive charge on carbon and CH bond. So the electrophilic substitution reaction is going to happen. Chlorine is orthopara directing or meta directing?
Orthopara directing.
Chlorine is orthopara directing. So you can substitute the ortho position or ortho position or para position. But out of ortho and para, which substitution is going to happen now? Para, because ortho will have more steric repulsions. So para is going to be substituted. So what you will get, students? You will be getting compound like this. Carbon is going to be connected to another carbon in this manner. We get CH, CCl3, CH, OH. Simple electrophile has been substituted. Actually, we form a VLAN complex, and that again undergoes to form this particular product. But we have written directly because this is an electrophile. Chlorine is ortho para directing, so we have written the para product. And now this para product will again be reacting with H plus ions because H plus are there in the reaction mixture. So lone pair of electrons are present on oxygen. The lone pair of electron present on oxygen, they will be attacking H plus to form this particular compound. CCl, CCl3, CH. OH is now going to be converted to OH2 plus. Okay, if you try to extend the reaction, chlorobenzene we have, and the chlorobenzene, not simple chlorobenzene, like on the para position you have substituted with the OH2 plus. OH2 plus H2O with the positive charge on oxygen is a good leaving group or not? OH2 plus is a good leaving group, so that will immediately leave to form the respective carbocation. We have CH, CCl3 with a positive charge. This is an electrophile which is actually substituted with the next molecule of chlorobenzene. Again, chlorobenzene is going to be ortho para directing, para substitution is going to happen, but now the electrophile is this one. So with respect to chlorobenzene, on the para position, you have CH group electrophile. CH group is connected with CCl3. CCl3. The CH is also connected with one more phenyl ring. Yes or no? And that, with respect to this phenyl ring, again chlorine should be on the para position. This is nothing but your DDT. DDT is actually obtained by just an electrophilic substitution reaction. Obtained by electrophilic substitution reaction of chlorobenzene with the chloral in H2SO4. Got this or not?
Yes.
Yes.
Or no? Dichloro, we got the same compound, dichloro, diphenyl, trichloroethane. Dichloro, diphenyl, trichloroethane, that is going to be the respective DDT, and it was used as an insecticide earlier. Now different other compounds have been prepared because this is found to be a little poisonous in nature. Okay, students, this will be regarding all reactions about your halogen compounds, alkyl halides, aryl halides, or haloalkanes, or derivatives of halogens, all have the same meaning. Just a second, we'll start with the alcohols, phenols, and ethers. Alcohols, phenols, and ethers, how are they prepared? How are alcohols obtained? By replacing the hydrogen of hydrocarbon with a OH group. Yes or no? How is halobenzene obtained, or how is haloalkane or haloarenes are obtained? Haloalkanes or haloarenes, they are obtained by replacing hydrogen atoms, replacing the hydrogen atoms of alkane with the halogen atoms, or arene with a halogen atom. But now alcohol, how are they obtained? They are obtained from alkanes by just replacing the hydrogens by some OH groups. Alcohols and phenols are formed when a hydrogen atom in hydrocarbon, aliphatic and aromatic respectively, is replaced by OH group. So that is how it is. The formula is written, but that's not like, it's not a preparation. If I ask you a question, how we can prepare alcohol? If you say, I'll prepare alcohol by replacing hydrogen with OH, that does not have any meaning, right? Does it have a meaning? So if I replace H by OH, I can prepare alcohol from alkane. No, it's not. It is not having any meaning. So I have to go with some mechanistic approach. Okay, the classification of alcohols. Then why you are defining the alcohols, phenols in this way? So we want to understand how the alcohol is, what is the molecular formula of alcohol. To know that if you try to replace the hydrogen of an alkane with the OH group, then the whatever the compound we get, that is said to be alcohol. Classification of alcohols and phenols. Alcohols and phenols may be classified as mono, di, tri, or polyhydric, depending on whether they contain 1, 2, 3, or more hydroxyl groups. Like if you take ethanol, if you have ethanol, only one OH group is there, so it is monohydric. Dihydric ethane 1, 2 diol, CH2OH, 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 CHOH, CH2OH, propane 1, 2, 3 triol, this is trihydric. Benzene 1, 3 diol, it is again dihydric. So based on the number of OH group present in the molecule, it is said to be dihydric, monohydric, trihydric, or polyhydric. More than 3 if you have, generally we call it as a polyhydric alcohol. Is that clear or not? Very simple classification only.
Yes, sir.
Right? Monohydric alcohols means all those alcohols which have one OH group. Monohydric alcohols can be further classified according to hybridization of carbon atom. Like if you talk about haloalkanes and haloarenes, there also we have done the classification based on hybridization. Hybridization of the carbon atom to which halogen atom is connected. So sp3 hybridized carbon can be connected to halogen. In that category we have alkyl halides, primary alkyl halides, secondary, tertiary, allylic, and benzylic. In all these, we have sp3 hybridized carbon connected to halogen. Where we have sp2 hybridized carbon connected to halogen? In which
Vinyl.
halides? Yes, vinylic and aryl. Yes or no? Same here, monohydric alcohols can be classified based on the hybridization of carbon atom. Here also can I say primary alcohol, secondary alcohol, secondary, tertiary, benzylic, allylic. All these are those species where carbon is going to be sp3 hybridized. First one, primary, secondary, and tertiary alcohols. In these types of alcohols, OH group is attached to primary, secondary, and tertiary carbon atom. Like primary alcohol means OH is connected to the carbon, which is connected to only one more methyl group. Secondary, OH is connected to the carbon, which is connected to two other alkyl groups. Secondary, it is also secondary, OH is connected to the carbon, which is connected to two other alkyl groups. Whereas if you look at the third case, OH is connected to the carbon, which is connected to three other alkyl groups. So it is said to be tertiary alcohol. So primary, secondary, tertiary alcohols. These are the alcohols where carbon is the OH is connected to the carbon, which is sp3 hybridized, and primary alcohol is having primary carbon connected to OH. Secondary alcohol means secondary carbon connected to OH. Tertiary alcohol means tertiary carbon connected to OH. Allylic and benzylic. This is your allylic carbon. The carbon next to carbon-carbon double bond system is said to be allylic. It is said to be allylic. And the carbon, the C double bond system next. This is again called as allylic. The carbon next to C double bond system is said to be allylic carbon. If to the allylic carbon OH is connected, then that is said to be allylic alcohol. Benzylic alcohols. These are the compounds in which OH group is bonded to sp3 hybridized carbon atom next to aromatic ring. Like OH is connected to this carbon, which is connected to aromatic ring, so it is said to be benzylic. It is also benzylic because OH is connected to carbon, which is connected to aromatic ring, so it is also called as benzylic. So allylic and benzylic alcohols also have the OH group connected to carbon, which is sp3 hybridized. And compounds containing sp2 carbon connected to OH. What are these alcohols? Can anyone name?
Vinyl.
Vinylic and phenol, we can say. Vinylic alcohols. In the vinylic alcohols, one of the carbon of carbon-carbon double bond system is directly connected to OH. And in the phenol also we can write. Okay. In the phenol also, OH is connected to the carbon, which is sp2 hybridized carbon. So vinylic alcohols and phenols, they are also coming under this category. That is, OH is connected to sp2 hybridized carbon and sp3 hybridized carbons. sp3 hybridized carbons are not connected to OH groups, they are slightly unstable because sp3 hybridized carbon is more electronegative. Oxygen is also more electronegative, so that bond is not going to be stable. Methods of preparations. How we can prepare alcohols from alkenes? To try to think of these preparations. Alkenes we have studied, right? Look at the different types of reactions which we have seen in alkenes. Any reactions you remember? Where you are getting alcohols as a products?
Oxymercuration,
Oxymercuration, demercuration. Very good. Next,
hydroboration,
hydroboration. Any other?
addition of water,
Addition of water. Very good. Addition of water occurs in the acid medium to increase the attack of pi electron density of alkene. So you will be getting addition of water occurs in acidic medium because H2 is also going to be a weak nucleophile. So as addition of water proceeds through carbocation intermediate. Pi electron density H plus, you will generate RCH plus CH2H, and now water comes into scenario. Lone pair of electrons on oxygen attack the carbon, generating RCH, CH3, OH2 with one lone pair and a positive charge. And lastly, loss of H plus occurs. Generate R, CH, OH, CH2H. So addition of water by acidic hydration of alkene, you can produce alcohols, and it proceeds through carbocation intermediate. Carbocation intermediate means rearrangements possible or not possible?
possible.
Possible. Okay, carbocation whenever it is obtained, rearrangements are possible. Hydroboration oxidation. What is the transition state here? Hydroboration oxidation. What is the transition state?
4-member cyclic ring.
Yes, very good. 4-membered cyclic transition state, and it will be proceeding through anti-Markovnikov rule or Markovnikov rule.
Anti-Markovnikov.
Anti-Markovnikov rule. You have to remember this. Don't need to write the mechanistic approach. And the rearrangements possible or not possible?
Not possible.
No rearrangements. Okay. No rearrangements. And from where you will be getting the hydrogen? Hydrogen will be obtained from BH3. OH will be obtained from H2O2 in the presence of OH minus. So we'll get anti-Markovnikov addition. So simply you can write RCHH, CH2OH. No rearrangements possible. Anti-Markovnikov rule addition. And 4-membered cyclic transition state is the intermediate, we can say. Oxymercuration, demercuration. Oxymercuration, demercuration. What is the transition state looks like?
Remembering.
Yeah, 3-membered cyclic transition states. No rearrangements. No rearrangements. Wherever we have carbon-carbon double bond, we have to simply add H2O to that. And no rearrangements. Markovnikov rule is going to be followed here. Markovnikov's rule. And hydrogen comes from where? H2O gives OH. Hydrogen is obtained from NaBH4.
NaBH4.
Okay, NaBH4 will be giving hydrogen. So these points we have studied in detail with the mechanistic approach also. Yes or no? If you remember. So oxymercuration, demercuration, hydroboration, oxidation, and addition of water to alkene in acidic medium. All these three are going to try to add water to the carbon-carbon double bond, and in their own way. So the products are going to be respective alcohols. So alcohols can be obtained from alkenes by hydroboration oxidation or oxymercuration demercuration or acidic hydration. Very good. By reaction of Grignard reagent with aldehydes and ketones, can we prepare Grignard reagents?
Yes.
Grignard reagent treated with the formaldehyde. What type of alcohol you get?
Primary.
Grignard reagent treated with any other aldehyde except formaldehyde, you get secondary. And Grignard reagent treated with ketone, you will be getting tertiary alcohol. The mechanistic approach we are going to write now. So CH3 MgBr. Let us write for the tertiary alcohol formation. treated with CH3, C double bond O, CH3. CH3 MgBr Grignard reagent can act as a base as well as nucleophile. It will act as a base when there is an acidic proton. Is there an acidic proton in ketone? CH3, C
No,
double
sir.
bond O, CH3? No.
No, sir.
No acidic proton. So CH3 minus will try to act as a nucleophile now. It will attack the electrophilic carbon and C double bond of pi electron density moves away. So negatively charged oxygen will try to develop electrostatic force of attraction with Mg plus, generating what, students? CH3C. This carbon is connected to one more methyl, CCH3, and O minus will be having electrostatic force of attractions with MgBr with a positive charge on magnesium. Now what happens? This we are treating with H plus in the presence of H2O. So O minus picks up the proton. So you generate CH3COH, CCH3CCH3. It is a tertiary alcohol. And MgBr reacts with water to form MgBrOH, and H plus is again lost. That H plus will again be used for the acidic hydrolysis of one more molecule. So these are going to be obtained. So with the formaldehyde, you get a primary aldehyde. With aldehydes, except a formaldehyde, except a HCHO, you get secondary alcohol. With the ketones, you will be getting tertiary alcohol. So Grignard reagent reacts with the aldehydes and ketones to form primary, secondary, and tertiary alcohols. And this was the mechanistic approach. And Grignard reagent is acting as a nucleophile because there is no acidic proton available. Right, students? By reduction using LiLH4, NaBH4, H2 in the presence of metal catalyst. Always remember, we are not going to discuss the mechanisms of reduction and oxidation because they are lengthy. So LiLH4 is a very good reducing agent. LiLH4 can reduce every functional group. Yes or no? LiAlH4, lithium aluminum hydride, can reduce all polar pi functional groups or all functional groups which contains polar pi bonds. NaBH4 will reduce how many functional groups? NaBH4. What are the functional
Four.
groups reduced by NaBH4? Yes. How many?
4.
4. Why they he? What are those?
So aldehydes, ketones, acid, halide, and imine.
Imine. Very good. LiLH4 reduces all functional groups containing polar pi bonds. NaBH4 reduces only 4 functional groups: aldehydes, ketones, imines, and acid halides. H2 in the presence of metal catalyst will reduce all polar and non-polar functional groups except H2 in the presence of metal catalyst is not used for the reduction of carboxylic acids. Okay, these points you have to remember, students. Lithium aluminum hydride, LiAlH4, Li plus AlH4 with negative charge on aluminum. It reduces all functional groups containing polar pi bonds. NaBH4, it reduces only 4 functional groups. What are those? We will be looking now. So oxygen containing functional group, that will be converted to alcohol. If you have a functional group like acid halide we have, that will be converted to respect to alcohol. Carboxylic acid we have, that will be converted to respect to alcohol whenever you treat with LiLH4. Oxygen containing will be converted to alcohol. Nitrogen containing will be converted to amine. Oxygen and nitrogen containing will be converted to also amine. Like if you have oxygen and nitrogen containing CH3, C double bond O, NH2 we have. We are treating this with amide is treating with LiLH4. You will get CH3, CH2, NH2. Yes or no? Oxygen containing will be converted to alcohol. Nitrogen containing will be converted to amine. So nitrogen containing means you can think CH3NO2. Treat with LiLH4. Nitro compound. Yes or no? Nitroalkane, that will be converted to CH3NH2. Nitrogen containing will be converted to amine. Oxygen and nitrogen containing will be converted to amine. and only oxygen containing will be converted to alcohol, CH3 C double bond OH. That will be converted to CH3 CH2OH. So lithium aluminum hydride will reduce all polar, like C double bond O is a polar pi bond, polar functional group. N double bond O, polar pi bond. C double bond O, again polar pi bond. LiAlH4 will reduce all functional groups which contain polar pi bonds, and oxygen containing functional group will be converted to respect to alcohol. Nitrogen containing will be converted to respect to amine. Oxygen and nitrogen containing, like amides, oxygen containing and nitrogen containing, they will be converted to respect to amines only. Lithium aluminum hydride reacts explosively with water and alcohols, like they can give LiLH4 in H2O or LiLH4 in ROH alcohol. They will react extensively and they form hydrogen gas, and that hydrogen gas is going to be added. And ether is commonly used as solvent for lithium aluminum hydride reductions. Whereas NaBH4, only 4 functional groups you can reduce. RC double bond O HR, that means aldehydes or ketones. RC double bond O X, acid halides. RCH double bond NH, imines. So sodium borohydride, that can reduce only 4 functional groups, and it can be used in water as well as in alcohol solvents. So LiLH4 in water you can give. NaBH4 in water also can be reduced for these functional groups. LiLH4 alcohol, NaBH4 alcohol, and the solvent can be ether. Everyone understood these points or not? You have to remember this, because mechanism you can't study for reduction reactions and oxidation reactions. It will be lengthier one.
Yes, sir.
Yes. H2 in the presence of metal catalyst. As I have told you, it reduces all polar as well as non-polar pi bonds. Non-polar pi bonds means alkenes, alkynes. There are non-polar pi bonds. It reduces all polar as well as non-polar pi bond containing functional group except carboxylic acid. Except carboxylic acid, it will reduce all polar as well as non-polar pi bonds. Oxygen containing is converting into alcohol, again same. Nitrogen containing will be converted to amine. Oxygen and nitrogen containing will be converted to amine only. So same conversion. If you have oxygen containing functional group, it will be converted to respect to alcohol. Nitrogen containing means it will form respect to amines. Both oxygen and nitrogen containing means it will form amines again. Look at the reaction. What is the product of this reaction, students? We have cyclohexanone. We are treating with LiLH4 or LiLH4 in the presence of ether or LiLH4 in the presence of water. I can give simple LiLH4, LiLH4 in the presence of water, LiLH4 in the presence of ether, or LiLH4 in the presence of alcohol. In all those conditions, what happens? First, look at the substrate. It has C double bond O. Polar pi bond is there. Yes or no? Functional group contains polar pi bond. It can be reduced to respect to alcohol. So you'll be getting what? Respect to cyclohexanol. Yes or no? Simple LiLH4 or LiLH4 in the presence of ether or lithium aluminum hydride in the water. You will have C double bond O converting into respect to COH. Okay, the C double bond O will be converted to OH. Here R C double bond R dash, what is it? It is an ketone. Ketone can be reduced with NaBH4. NaBH4 reduces ketones. So it will form what? Respect to alcohols. So what are the compound you are going to get? RCHOH R dash. RCHOH R dash. RC double bond H. H2 in the presence of palladium. It will form what? H2 in the presence of palladium. H2 in the presence of metal catalyst will reduce all polar and non-polar pi bonds except carboxylic acid. Is it a carboxylic acid? No. So it will be
Yes.
reduced by H2. You will get what? Alcohol. So you get RCH2H. RCH2H is going to be obtained. Like for oxygen and carbon, we are adding hydrogens. That's it. For oxygen and the carbon, we are removing the pi bond and adding hydrogens to carbon as well as to oxygen. Is that clear, students?
Yes, sir.
Yes, right. R C double bond OH, and we are treating this with LiLH4 in the presence of H2. It is carboxylic acid. Lithium aluminum hydride will reduce carboxylic acid or not?
Yes.
Yes,
Yes, sir.
only H2 in the presence of metal catalyst will not reduce. So lithium aluminum hydride will reduce. So you try to add hydrogens. So simply RCH2OH you will get. That is primary alcohol. So we have add hydrogen here, add hydrogen here. You get RCHOH and OH, 2OH on the same carbon unstable. Again, it will be converted to RC double bond OH. Again, you add hydrogens, you will get RCH2OH. Directly, you get alcohol. RC double bond OR dash, lithium aluminum hydride, H2 in the presence of palladium. What you are going to get? Lithium aluminum hydride will reduce esters. H2 in the presence of palladium, that will also reduce. That will also reduce esters. H2 in the presence of palladium will not reduce carboxylic acid, but it will reduce esters. You get what? Alcohol. So this bond is going to be cleaved. You get RCH2OH and R-OH. In the ester, CO bond is going to be cleaved, generating RCH2OH. You add hydrogens to this carbon, this oxygen. Again, double bond is there, right? So this bond, whenever you're cleaving, again add hydrogens to this oxygen as well as this carbon. You get like this pi bond, whenever you're cleaving, you are adding two hydrogens, one to carbon, one to this oxygen. This carbon oxygen bond, whenever you're cleaving, you are adding two hydrogens, one to carbon, one to oxygen. You are getting R-OH and RCH2OH. RCH2H plus R-OH. Is that clear, students?
Yes, sir.
Yes, right. Similarly, next methods of preparation is methods of preparation of phenol. So after the methods of preparation of alcohol, like from reducing agents, from Grignard agents, from alkenes, we can also look at the methods of preparation of phenol. From haloarenes, how we can prepare? Just now we have seen in today's lecture only. SNAR, Dow's process. Yes or no? So if you are simply taking chlorobenzene, we have to treat with NaOH at a very high temperature and high pressure. High temperature and pressure are required because there was no electron withdrawing group at ortho and para positions. Okay. This proceeds through SNAR, that is addition elimination type mechanism. Addition elimination type process. Chlorobenzene plus NaOH, 623 Kelvin, 300 atmosphere at a H plus, you will be getting respect to phenol. So that is going to be obtained. Chlorobenzene, if you treat with NaOH at high temperature, you get sodium phenoxide first. And that sodium phenoxide upon acidification forms respect to phenol. And this total process is said to be Dow's process. Same SNAR mechanism, addition elimination type. And what is the complex form? Mason-Hammer complex, which is similar to your carbanion system. From benzene sulfonic acid also we can prepare. Benzene sulfonic acid, can anyone remember how we can prepare from benzene sulfonic acid? From benzene sulfonic acid, how can we prepare your respect to phenol? Yes, anyone? So if you treat the benzene sulfonic acid with NaOH in the presence of H plus, you will be getting respect to phenol. So how to generate benzene sulfonic acid? From benzene you can do the reaction. Benzene treated with oleum. Oleum is what, students?
SO3.
H2S2O7, or you can say this as H2SO4 plus SO3. SO3, this will be acting as a respect to electrophile. So the pi electron exchange, this is an electrophilic substitution reaction. S double bond O, S double bond O, S double bond O, S double bond O, S double bond O. Pi electron is attack the sulfur. The S double bond O pi electron entity moves away. You will generate S O minus, S double bond O, S double bond O, positive charge here and OH bond. Negative charge on oxygen picks up the proton. You will generate respect to benzene sulfonic acid, S double bond O, S double bond O, OH. This benzene sulfonic acid, whenever you treat with NaOH at higher temperature, again addition elimination type mechanism is going to happen. Upon acidification, you get phenol. Okay. This upon treat with NaOH, OH minus is going to substitute on this particular carbon. Same, similar to your addition elimination type. Similar to SNAR. Addition elimination type reaction is going to happen. So again, you are getting respect to OH and SO3H, whatever it is lost, that will pick up the proton. Yes or no? The SO3H is actually undergoing a loss. That will again, the positive charge, whatever you have, that will try to pick up the proton. That removed SO3 again acts as an electrophile for the next molecule. Like that, the reaction proceeds. Is that clear, students? From
Yes.
Dow's process, like from halobenzene, you can prepare respect to phenol. From benzene sulfonic acid, how we can generate benzene sulfonic acid? By treating benzene with oleum. Oleum is H2S2O7, or you just take H2S4 and SO3. You will generate benzene sulfonic acid. That upon treatment with NaOH at a very high temperature like 350 degrees Celsius, and after acidification, it forms respect to phenol. That will also be undergoing a mechanism similar to SNAR. And any other process you can remember? From halobenzene we have prepared. From benzene sulfonic acid we have prepared. Any other process can you think of?
So from cumene.
Yes, from cumene. From cumene, how you can prepare? This is the industrial method of preparation of phenol. Cumene, upon treatment with O2, it forms respect to cumene hydroperoxide, and this is happening because of some peroxy reaction, that is free radical path. This cumene hydroperoxide upon acidic hydrolysis forms respect to phenol and acetone. And what was the mechanistic approach of this? First step is simple. So whatever the cumene we have, so that will lead to the formation of respect to free radical in this fashion. Yes or no? And whatever O double bond O we have, that will be converted to O dot double bond OH. Like double bond is now going to be converted to single bond. Like oxygen double bond oxygen, how we can treat? Oxygen double bond oxygen in the free radical mechanistic approach, I can see oxygen single bond oxygen with one odd electron on each oxygen. Can I write like that? We can obviously write, right? So CH bond also we can imagine the CH bond homolytic cleavage I am doing. One electron I am giving to carbon, other electron to hydrogen. So the hydrogen H dot is now reacting with O, that is oxygen, to form OH bond, and oxygen will have one free radical, that is HOO dot. That HOO dot will be reacting with this carbon. The free radicals are going to be combined. You are generating respect to cumene in this fashion. That is cumene hydroperoxide is obtained. CCH3, CCH3, carbon connected to oxygen, oxygen single bond and OH. This is nothing but your cumene hydroperoxide. This will happen at high temperature or sunlight, free radical path. And this cumene hydroperoxide, we are doing acidic hydration or acidic hydrolysis. So we have oxygen where we have lone pair of electrons on both the oxygen atom. The peroxy bond is stable bond or slightly unstable. The peroxy linkages are unstable. Why? Because of repulsions between the lone pair of electrons. So can I say lone pair of electron present on oxygen that picks up the H plus? Yes, it can happen. So as soon as it picks up, you will get phenyl ring connected to carbon, 2 methyls as it is, and you have oxygen. Like you can write instead of phenyl, I'll write as of now. Next step, I'll write pH. Oxygen, this oxygen will have 2 lone pairs. For the other oxygen will have only 1 lone pair. What happened to the other lone pair? It has been lost in the new bond formation. That is net electron density on this the second oxygen that has been used up to form a new bond, new OH bond. So we get that oxygen with the oxygen will be having a positive charge. Now can I say this oxygen with the positive charge is going to be unstable and H2O is a very good leaving group. So this oxygen electron density will be moving toward the other oxygen greatly. Because of that, this oxygen develops what charge?
Partial positive.
Partial positive. Because the partial positive charge on this oxygen is stable or unstable? Unstable. So the phenyl shift happens instantaneously, then only the oxygen cleavage happens. The phenyl shift happens instantaneously. Just a second. I'll just add an extra slide so that you can draw the complete mechanistic approach. Yes. So the phenyl shift, whatever we are thinking of, that will happen instantaneously. So we have this compound, right? Carbon, CCH3, CCH3, oxygen with 2 lone pairs, and other oxygen with only 1 lone pair, positive charge, 2 OH bonds. Now the phenyl shift happens. You may ask a question, sir, why can't the methyl shift happen? What is the order of shifting? Hydrogen will be having greater shifting than aryl, then alkyl. You are doing a lot of shifting in carbohydrate intermediate, right? Whenever you have two possibilities, you can do the hydrate shift or aryl shift or alkyl shift. Then you have to look at this migratory order. This is the migratory order. So aryl group will be shifting greatly. That is phenyl shift happens. So you will be generating CH3 connected to carbon, carbon connected to CH3. This carbon phenyl has been shifted, so you get a positive charge, and oxygen 2 lone pairs, and oxygen connected to phenol, and you have H2O lost, and you have H2O lost. Whatever the H2O lost, that can now again attack us or not. Whatever the H2O which has been lost, that can also attack. How it can attack, students? Whatever the H2O lost, that can attack as a nucleophile. Yes or no? The H2O, whatever it is there, that can be attacking as a nucleophile. Lone pair of electrons on oxygen will try to attack this particular carbon. As soon as they attack, the positive charge on the carbon is nullified. You generate CH3, CCH3, OPH, and H2O attack. So oxygen will have only 1 lone pair positive charge, 2 OH bonds. And a positive charge on oxygen is unstable, so OH bond is going to be cleaved. So loss of H plus occurs. You will generate CH3, CCH3, COPH, and oxygen will have only 1 lone pair and 1 OH bond, and a positive charge on oxygen is going to be nullified. Why? Because lone pair, the OH electron density is moving towards oxygen. Hydrogen develops partial positive. That partial positive charge hydrogen is attacked by lone pair of electrons on this oxygen. So you get OPH, right? That oxygen will now have only 1 lone pair and 1 pH and 1 hydrogen and a positive charge. Positive charge on oxygen is unstable. Again, the CO electron density is moving. So lone pair of electrons on this oxygen comes into resonance. If they come into resonance, what is going to happen? You generate CH3, CH3, C double bond O, oxygen only 1 lone pair, now a positive charge on oxygen, OH bond. As soon as they come, you have the CO bond cleaved. So PHOH will generate, and this will ultimately give, upon loss of H plus, gives what? CH3, C double bond O, CH3, and PHOH is nothing but phenol. PHOH is nothing but phenol. Everyone got the mechanistic approach or not? I am giving the mechanism so that you can understand how the things are happening, but it doesn't mean you always have to write the mechanism. No, you can directly write the products. Cumene isopropyl benzene forms cumene hydroperoxide. Upon acidic hydrolysis of cumene hydroperoxide, you get phenol and acetone. Okay, acetone is obtained as a side product, which can also be used for different other purposes. Is that clear, students?
Yes, sir.
Yes, right. Now next process from benzene diazonium salts. I think I have explained the mechanism of this benzene diazonium salt yesterday. From aniline treated with NaNO2 in the presence of HCl. Remembered or not?
Yes, sir.
Aniline, if you
Yes, sir.
treat with NaNO2 in the presence of HCl, it will form respective benzene diazonium salt, N2 plus Cl minus. this N2 plus Cl minus is not so stable. But why you are preparing this? What is the advantage of preparing N2 plus Cl minus? Benzene diazonium salts. Benzene diazonium chlorides or benzene diazonium salts are used to actually place a nucleophile on the electron-rich benzene ring easily. Electron-rich nucleophile substitution on a aryl ring is very difficult or not, because the benzene ring already have pi electron density, nucleophile is electron-rich. Placing the nucleophile on a electron-rich benzene ring is difficult because of repulsions. Whenever you proceed through this benzene diazonium chloride, you can easily place the nucleophile, because the N2 gas is going to be released here, which is going to have a more stability and which will also increase the entropy of the system. Along with this, HCl is produced. So aniline, whenever you treat with NaNO2 and HCl, the temperature has to be 0 to 5 degrees Celsius. If the warm is just at 10 degrees, at 10 degrees Celsius only, you will be getting the benzene diazonium chloride undergoing hydrolysis to form phenol, and N2 gas and HCl is evolved. Aniline, NaNO2 in the presence of HCl forms respective benzene diazonium chloride, and that upon light warming with water like 10 degrees Celsius only, it forms phenol and N2 and HCl. And in the mechanism, what is the electrophile? What is the electrophile, students?
NO2 plus, NO plus.
What is that? Nitrosonium ion, N double bond O plus is the electrophile obtained, also called as nitrosonium ion. And this is also a method of identification between primary, secondary and tertiary amine. Primary amine will react with NaNO2 in the presence of HCl to form respective benzene diazonium chloride, whereas secondary amine react with NaNO2 in the presence of HCl to form what? To form yellow oily liquids. We'll discuss that in detail in the nitrogenates compounds. If you take a secondary amine, it will not form benzene diazonium chloride. Rather, you will get a N double bond substituted. If you take tertiary amine, what happens? If you take this secondary amine, like instead of NH2, I take NHR. Treat with same NaNO2 in the presence of HCl. You get N double bond O R. Lone pair of electron present on nitrogen, they are going to attack the electrophile, forming N double bond O with a positive charge on nitrogen, and NH bond is going to be cleaved. It is an yellow oily liquid. So what you are getting is N-alkyl, N-nitroso, N-alkyl aniline is going to be obtained whenever you treat with secondary amine. With the tertiary amine, what happens? Like tertiary aromatic amine I have taken. If tertiary aromatic amine is taken, you will be having electrophilic substitution happening. Treat with NaNO2 in the presence of HCl, you will generate the NO placed at para position. Ortho para directing group, right? Lone pair of electrons on nitrogen is a electron donating group, which is ortho para directing. At the ortho position, if you do the substitution, steric repulsions are more. So on the para position, you have substitution of NO and NRR will be as it is. RR dash you can take, which is an example of, it is an electrophilic substitution reaction. So primary amines primary aromatic amines react with NaNO2 in the presence of HCl to form benzene diazonium salts. Secondary amine reacts to form N-nitroso N-alkyl amine or N-nitroso N-alkyl aniline. Tertiary amine will react with NaNO2 in the presence of HCl to form respective para substituted para nitroso N N dialkyl aniline. That means tertiary amines undergo electrophilic substitution reaction, not the electrophilic nucleophilic attack. Okay, so that is how it is actually used to characterize between primary, secondary and tertiary anilines, that is aromatic amines, right? After the preparations of phenol, students, phenol you have prepared from Dow's process, from cumene, from benzene sulfonic acid, and also from diazonium salts. After that, you can go with the physical properties, boiling point. Generally, this is the order of boiling point. Carboxylic acids will be having greatest, then alcohols, then ketones, then aldehydes, then ethers, and then alkanes. Why the carboxylic acids will be having the greatest boiling point? Because of extensive hydrogen bonding. For carboxylic acids, which are actually existing in the form of dimer, I think I have told you one concentration term. Which concentration term is used for carboxylic acids?
Formality.
Formality you are going to use. Very good. After carboxylic acid, you have alcohols will have highest boiling point because of more intermolecular force of attraction. Then ketones, aldehydes. After aldehydes, you can have Ri and RBr, like alkyl iodides and alkyl bromides. After that, you have ethers, and after ether, you have alkyl fluorides and alkyl chlorides, and the least is going to be alkanes. And this is true for only similar molecular mass. I cannot say I cannot take an alkene with 10 carbons and a carboxylic acid like ethanoic acid, and I cannot compare. Yes or no? For similar molar mass, if the molecular mass is almost same, then in that case, this is the order of respective boiling points. Carboxylic acids will have highest, then alcohols, ketones, aldehydes, then alkyl iodides and alkyl bromides, then ethers, then alkyl fluorides and alkyl chlorides, then alkanes. This is for similar molecular mass species. For similar molecular mass species. Obviously, if molecular mass is increased, molecular mass increase means boiling point will also increase. Boiling point is directly proportional to molecular weight, because molecular weight is directly proportional to van der Waals force of attraction. Okay. So this is the acetic acid, like molar mass you compare 60, 60, 58, 58, 60, 58. That means almost same molecular mass. So boiling point order, acetic acid greatest 391, then propanol 370, then acetone 329, propanol 322, methoxymethane ether 281, N-butane 273. Okay, this is how the boiling point is going to be varying. Boiling point purely depends upon intermolecular force of attractions. Carboxylic acids are higher boiling liquids than aldehydes, ketones, and even alcohols of comparable molecular masses. This is due to more extensive association of carboxylic acid molecules through intermolecular hydrogen bonding, and they exist as dimers even in the vapor phase. That is important. Even in the vapor phase, the intermolecular force of attraction is still there. That is why they are going to be having greatest boiling points. Okay. So this is how the partial negatively charged oxygen develops attraction with partial positively charged hydrogen. Partial negatively charged oxygen from C double bond O develops a electrostatic force of attraction with the partial positively charged hydrogen. Due to this intermolecular hydrogen bonding, like two hydrogen bonding sites are there. Two hydrogen bonding sites stabilize greatly, and thus dimer is formed. Is that clear, students?
Yes, sir.
Yes, sir.
Yes, right.
Yes, sir.
Try to compare here example. First example, A and B. You try to give the order. A, B, C. Second example, A, B, C. First example, try to give the order. Boiling point, arrange A, B, C in the boiling point order. Correct order of boiling point. First A is alcohol. First one will be A, then B, and then C, because molecular mass is same. Molecular mass is almost same. Not I am saying exactly same. Molecular mass is almost same. So for almost similar molecular masses, alcohols will have high boiling point, then ethers, then alkanes. Same. A will be great, then C, and then B for the second. Boiling point of alcohols. Boiling point of alcohols is directly proportional to intermolecular force of attraction, which is directly proportional to molecular weight, and which is inversely proportional to branching. Because if branching is high, what happens? If branching is high, in that case, you will be having the spherical shape acquiring. If the spherical shape is acquired, whenever we have a spherical shape, there the van der Waals force of attraction are going to be decreased. Compare here, students, ABC.
ABC.
Greater than BC, greater than C.
ACB.
ACB, why? Branching great no in C.
Sir, because A has largest molecular mass, right?
Yeah,
Five
A is
carbon.
greatest because of molecular mass. 1, 2, 3, 4, 5. 5 carbons are there. Compare among B and C.
B then C.
Yeah. A, B, C. Because A will be having greater molecular mass. So greater molecular mass will be, first you have to compare. So A will be greatest. When you're trying to compare between B and C, B will be greater when compared to C. Because in C we have branching. In B we don't have any branching. So A, B, C will be the right order. Okay, students, this is about the physical properties like boiling point of alcohols. Next, we have chemical reactions of alcohols. Next class, we'll discuss about different types of chemical reactions of alcohols. Okay. Thank you all, everyone. Bye.
Thank you.
Thank you.
Thank you, sir.
Mm.